Example number 1. A garden is to be laid out in a rectangular area and protected by chicken wire fence. What is the largest possible area of the garden if only 100 feet of chicken wire is available for the fence? First, we'll sketch the rectangle, as I've done here. And the goal of the problem is to, let's see, what is the largest possible area? So the goal is to find the maximum area. And the first thing I want you to do is write what we're trying to achieve. The maximum area. An area of a rectangle, as you know, is length times width. I'm going to arbitrarily identify some variables. We'll call the length here x and the width y. And so we'll write the area equals x times y. But we desire the area to be a function of one variable. So what we need to do is use some of the information to put maybe y in terms of x or x in terms of y. And as you see here, it says the 100 feet of chicken wire fence. So that's the perimeter. So as you know, 2x plus 2y is the perimeter, and that is going to equal 100. So if we simply solve for y here, so y equals 50 minus x. So we're going to write area now as a function of x. So area is the length of x times the width, 50 minus x. I would also like to discuss the domain at this point, because that's a very important element. And let's first say, what is the smallest that this side can possibly be? Well, it can't be 0, it wouldn't be a side, so it has to be greater than 0. So in our domain, we want to say that x has to be bigger than 0. But what is the largest that the side can be? Well, it couldn't be 51, because if the side were 51, then y would be negative, and that's not possible. So x has to be less than 50. It can't equal 50. For the same reason, this would not be a side at all. So the domain is between 0 and 50, not including those endpoints. I'm going to go ahead and distribute here to make it a little easier to work with. So it's 50x minus x squared. That is the function that we wish to optimize, maximize to be specific. So now in our analysis of max and min, we always take the first derivative. So a prime of x is going to be 50 minus 2x. And of course, you know you need to set that to 0 to find the critical point, or critical points. In this case, x equals 25. So now I can be fairly confident that this is the answer to where the maximum is going to occur. But I just want to make double sure using some of the rules we learned previously. So I'm going to employ the second derivative test. By taking the second derivative of our function, we now get the second derivative is always equal to -2. Now if I evaluate the second derivative at my critical point, it will still be negative, which is important because it's less than 0. And because it's less than 0, we say therefore normally a has a relative max, but here we're going to say a has an absolute max at x equals 25. Now why absolute max? Well, there is only one critical point. And at that critical point, we found that it's concave down. So not only is it a local max, it must be the absolute max. And we still have not answered the ultimate question. And the question here, if I scroll up just slightly, it says max what? Not where. The where is 25. The what is the maximum area? So to find the maximum area, this is the answer now. To find the maximum area, we want to take this critical point and plug it into our function. And so we're going to get 25 times 25. That's here. I actually plugged it into this one. And that's going to be 625 squared feet. that answers the question. What is the absolute maximum area? 625. Where is the absolute maximum area? X equals 25 feet. So you can see the importance of the where or what. Let's just do an illustration of that. Fun example. Let's say I'm a waiter and I make tips Monday, Tuesday, Wednesday, Thursday, and Friday. On Monday I made $20 in tips. Tuesday I made $50 in tips, $30 in tips, $40 in tips, $100 in tips. If I ask the question, what is the most amount of money I made on any given day, what would be 100? If I said, what is the most amount of money I made on any given day, and you said Friday, well, that's not really answering the question. Now, if I ask the question, on what day, where, on what day did I make the most amount of money, then the answer would be Friday. Similarly, let's take a look at this tip schedule. If I said, what is the most amount of money I made? There's only one answer. The most amount of money that you made is $100. Doesn't matter that it happened twice. That is the most amount of money you made on any given day. But if I ask the question, where is or on what day did I make the most amount of money? Then there would be two answers, Wednesday and Friday. Example number 2, a box, an open box, no lid. An open box is made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the corners and bending up the sides. What side should the squares be to obtain a box of largest volume? Okay, first of all, an open box, no lid. So that means I could put items in this box and you would see them. I can stack them high. These would be in there like this. Okay, so open box, that's what we desire. It's a pretty ridiculous box design that they want, because they're going to take a rectangle piece of cardboard and they're going to cut out squares from the corners. Okay, see that? Now they're supposed to all be equal sizes. And then they're going to fold it along this line up, fold it along this line up, fold it along this line up, fold it along this line up. This problem makes me laugh because if you folded it up, these would keep falling down. So you would need a lot of duct tape. This is a little bit of a ridiculous problem, but the idea is how to set up an optimization problem. Okay, this is the where, not what. This answers are like Tuesday, Wednesday, Friday. Where, not what is the maximum volume, but where does the maximum volume occur? So the objective is to maximize volume, and the volume of a rectangular box is length times width times height. So let's take a look at this now. Okay, so this entire side of this rectangle here, let's just say this is the 30-inch one. That's fine and dandy. What we desire is this here, which is the result of folding it up, which is this here. So what size square are we going to cut from this cardboard? We don't know. So I'm going to call the size of the square x. X by x, x by x, so on and so forth. So if I'm cutting out that square x by x, then this side here is no longer 30, but it's going to be 30 minus 2x. Similarly, this side here is going to be, well, let me find it, 16 minus 2x. All right, so our volume in terms of x is going to be the length, 30 minus 2x, the width, 16 minus 2x, and the height. So if we fold that up, this becomes the height, x is the height. Going to distribute to make our life easier, and that's going to be 4x cubed minus 92x squared plus 480x x. It's important again to define the domain of the function v. Okay, well, what size can x be? Clearly x has to be bigger than 0. Then we want to look at the sides. Well, for this side here, 15 would be the largest it could be, because at 15.1 or 16 we have a negative side. So we know we have to be less than 15. If we look at this side here, it certainly cannot be 8 or bigger than 8, so we're restricted by 8. It cannot equal 8, but has to be smaller than 8. Well, it has to be smaller than 15, and it has to be smaller than 8, so we have to take the more restrictive one and say that x is smaller than 8. So the domain of this function is that x is going to be between 0 and 8, not including the endpoints. Let's take the first derivative. V prime of x equals 12x squared minus 184x plus 480. We set that equal to 0. I'm going to help by factoring this for you, and this factors to 4 times the quantity x minus 12 times the quantity 3x minus 10, and we set that equal to 0. This gives us two critical points. X is equal to 12, or x is equal to 10/3. Do you notice something? That the x equals 12 is out of the domain, so we don't consider that. We'll do the second derivative test to prove, or at least verify, that the absolute max is going to occur at x equals 10/3. So I take the second derivative. Now the second derivative is going to be 24x minus 184. We evaluate the second derivative at our critical point, and that's going to give us 80 minus 184. Not sure exactly what that is. I don't really care, because I can see that that is clearly less than 0. And therefore, V has an absolute max. I say absolute again because there's only one critical point on our open region, and I found that it's concave down at that critical point. So V has a max at x equals 10/3. This also answers the question where it occurs where. So the answer to the question is 10/3 by 10/3 inch squares. Example number 3 is a technology question. A rectangle is to be inscribed under one arc of the cosine curve. Now this is real life. What is the largest area the rectangle can have? Okay, let's start off with a sketch. Not necessarily with technology, but in our mind, we should know what the cosine curve looks like. Okay, it comes up like this, comes through, and then continues on over here. That's one arc of the cosine curve. Now we want to inscribe a rectangle, so let me do that. This is an even function, so it should be symmetric about the y-axis. And there's the rectangle inscribed under the cosine curve, one arc of the cosine curve. Now, before we use technology to go further, I want to identify the coordinates of this point, and this is a really important coordinate. It's going to help in a lot of ways. Okay, the coordinate is on the x-axis, it's just going to be the x value. And then the y-coordinate, because it touches the curve, is going to be the function itself. So the cosine of x. So those are the coordinates of that ordered pair. We want to maximize area. Okay, and the area, as we know, of a rectangle is going to be the base times the height. Area in terms of the variable x is going to be the base. Now let's analyze this carefully. The base is not just this value of x. See, x is the distance from 0 to this point. So the base is not just x, the base is going to be 2x. And then the height of the curve, the height of the rectangle is going to be the y-coordinate of the curve. So the height of this is going to be cosine of x. We can also define the domain without technology. This value of x, remember, x is the distance from the origin to the end of the rectangle, so this value of x has to be bigger than 0. And because it's inscribed under one arc, the value of x has to be less than the 0 of the cosine curve. And we know that cosine of x has a 0 at pi over 2. This will assist us when we graph the function and help us to set the window range. So now let's use some technology. Let's go to our y menu and let's define y1 to be this function. So I'm going to write 2x. Now if you recall from earlier, if I don't put this multiplication symbol in, it might not recognize 2x and cosine of x as different functions. So I'm going to insert the multiplication symbol. I now want to graph the derivative of this function because I want to find where the derivative is equal to 0, and I'm going to use the graphing features on the calculator to do this. To review, we'll go to our home screen and we will find the derivative of y1 of x with respect to x. That will report an answer. We're going to copy that answer. We're going to go back into our y equals menu, and for y2 we're going to paste the answer. When we graph this function, the derivative function that is, making sure to set our x from 0 to pi over 2, here's our x-axis. The function that we graphed should look something like this. Again, this is the derivative function. And you can see here that the derivative goes from positive to negative at this 0. So take a moment and find that 0, F5, 0, left to right bound, and we're going to report that answer. That's important up here. So a prime of x equals 0 at x equals, hopefully you found that to be 0.860, shown down below also. And now the a function is not only locally maximum at x equals 0.860, it is also the absolute max. So I want to discuss that here for a second. So here, this is a prime of x greater than 0, and below we see that a prime is less than 0. And what we'll say now is that a prime of x is greater than 0 on the open interval 0 to 0.860. A prime of x is less than 0 on the open interval 0.860 to pi over 2. And since it's greater than 0 to the left always, and less than 0 to the right always, a has a absolute, but I'll just write max, at x equals 0.860. And I'll throw in the therefore. Now again, this question answers the Wednesday. When will the area be maximum? What we want to find is, what is the absolute maximum? So I want to find the answer, so I'll write answer. And I want a of 0.860, and I'm going to let technology give me this answer. In theory, what I'm doing is taking this number and plugging it into my area function. But you see, since we already have y1 defined, I can, in my home screen, ask for y1 of 0.860. And that should return 1.122, whatever units, squared. That is the absolute maximum area of a rectangle that can be inscribed inside one arc of the cosine curve. Example number 4, another inscribed question. This time we're going to inscribe a can inside a cone. Find the radius and height of a right cylinder of largest volume that can be inscribed in a right circular cone with radius 6 inches and height 10 inches. Let's take a look at that picture. So to draw this, I'm going to draw an upward caret. I'm going to draw a circle beneath it to draw my cone. Now I have to draw a can inside the cone. So I'll come over here and I'll draw an oval circle. I'll drop straight down, and draw another oval. Okay, so the container, this is like related rates. The container's dimensions are fixed. This one is fixed at 10 inches. And the radius of the white container, the cone, is 6 inches. The can's dimensions, on the other hand, are to be determined. So right now we have to label the radius as simply r and the height as h. You can use other variables. I just like the r and h because I know formulas that involve r and h. The objective is to maximize the volume of a can. The volume of a can is going to be pi r squared, that's a circle, times the height. You see here we have two variables, r and h, and that's not desirable in our quest to find local max or min. So we need to find r in terms of h or h in terms of r. This is a little bit tricky. I'm going to look at a cross section. So this dimension is 6 and this dimension is 10. Now if I look at the can goes like this and like this. So this is r and this distance here is h. Now we're going to be using similar triangles, but it's really important that you identify what the similar triangles are. We have a couple that we can choose. We can have this triangle here, which is in red, and that triangle will be similar to the triangle that I will outline here in yellow. That's one option we have. Another option, if I take, let's say, a pink color, I see that this rectangle here in pink, triangle here in pink, will also be similar to the triangle in yellow. So we get to choose which ones we want to set up a proportion with. For me, I chose to use the red triangle to be similar to the yellow triangle. The yellow has the dimensions 6 to 10. The red has the dimensions, well, this is where it gets a little tricky. This one here is clearly r, because this is r is r. But this height here is not h. See, this height here is h. The height we desire over here is not h. The height we desire there is the difference of 10 and h. So this is going to be 10 minus h. And this is the part that often trips people up. So we are ready now to set up a proportion, and we have a variety of ways to do this. For me, I'm just going to say altitude is to radius of the large is going to equal altitude to radius of the small. From that, I can cross multiply. 10r equals 16 minus 6h, and I can choose for one in terms of the other. I'm going to choose to solve for h in terms of r, and that will be 10 minus 5/3 r. So my function that I wish to optimize, volume, will be volume in terms of r, pi r squared, and then h, but h we saw was 10 minus 5/3 r. Now everything is in terms of r, and this is desirable. Let's take a look at domain. Well, clearly the r has to be bigger than 0, but the r also has to be less than 6. I will distribute, and now I will find the derivative, v prime of r. So we'll have 20 pi r minus 5 pi r squared, and we want to set that equal to 0. Factor. We have two zeros, r equals 0 or r equals 4, but the r equals 0 is out of domain. One critical point, and with the non-technology questions, I prefer the second derivative test to verify. And the second derivative is 20 pi minus 10 pi r. The second derivative at 4 is 20 pi minus 40 pi, which is clearly less than 0, and therefore v is absolute max at r equals 4. The answer wants this dimension, r equals 4 inches, and we have to compute what h is, and h is going to come out to be 10 minus the 5/3 times the 4, also inches. This answers the question. What are the dimensions that will give us the largest volume? We're not finding that largest volume, we're just finding where that largest volume occurs.